And one assumption that seems to draw a lot of attention, at least every first-year postgraduate student that takes a course on information retrieval seems to want to tackle that assumption. That just assumption somehow gets under people's skin. They think that it's a horrible assumption that you're saying that the words are mutually independent, and it is false, right? And it seems like you should be able to do better, right? Because we know how to build conditional models. We know how to condition the probability of one event on the on another event happening or not happening. So we should be able to encode those dependencies in there, and it should magically make our retrieval systems a lot better than they are today. So let's look at what's been done with that. That assumption is there in the classical model. It is blatantly false. It's probably the most widely criticized assumption. And the first attempt to get rid of it dates back to 1977, around the same time that PRP, that the probability ranking principle was developed, and the first version of the classical probabilistic model appeared. So it's almost immediately people started nibbling at this. So the first model is to say, well, let's not go for sort of all-out dependence. Let's take it one step at a time. Let's introduce first-order dependence into the model. So first-order dependence, we're going to condition. We're going to create dependencies between pairs of words. So if you're trying to build a directed model out of this, so what you're saying effectively is you're saying each word, I'm going to condition it, the presence or absence of each word, I'm going to condition it on the presence or absence of a parent word. So each word is going to have a parent, and I'm going to condition the dependency between the word and its parent. So if I had a set of words, I could encode dependencies like that. And Rijsbergen chose to encode dependencies as a spanning tree, right? So he wanted to have a connected graph, and he didn't want to have any loops. You could try to do it in other ways, but that seems like a reasonable assumption, right? So you're basically connecting words in a graph, and for each word there's going to be a parent, and whether or not the word appears is going to depend on whether or not its parent appears in the document. And you can have different probabilities for the relevant and the non-relevant class, naturally, otherwise you wouldn't be able to rank documents very effectively. It's a nice model, it's straightforward. By the way, don't try to make sense of the dependencies in this graph. They're just off the wall, so there's no deep meaning why drink depends on likes. What are the nice things about the model? Well, it's fairly simple. You can estimate a spanning tree like that just by computing mutual information between word occurrences, and it's a fairly tractable thing to do, and you end up with a model that is reasonably compact as well. The total number of parameters in that model is only twice the number of parameters in the original model. Remember, in the original model, for each word, we had two parameters, PW and QW, the probability that occurs in the relevant set and in the non-relevant class. Okay? Now we have 4 parameters for each word, and that's the probability that it occurs in the relevant class given that the parent is present in the document, and the same probability PW given that the parent is not present. And the same thing for QW. I now have one QW for when my parent is present in the document, and another QW for my parent for when my parent is not present. So the total number of parameters is only twice as much. You haven't squared the parameter space. Squaring it would make things infeasible because you're dealing with word space. Your number of parameters is huge, so squaring it would you wouldn't be able to estimate anything. But this is still sort of sensible. So how would you use this model to compute a probability for the document? Well, if I had a document that said he likes to wink and drink pink ink, the way you would do that is you would effectively, starting from the root, you would enumerate the probabilities one by one. So, by the way, in the previous model, in the classical model, you would just say it's the probability of he times the probability of likes times the probability of two, and so on and so forth. So now you're saying it's the probability that likes is present in the document times the probabilities that 2 is present given that the likes is present. Why? Because 2 is likes is a parent of 2 in my MST, in my tree, and likes was present in the document. So I condition the presence of 2 on the presence of likes. So on and so forth, everything below that is pretty much the same until you get to that point. Right? That document doesn't contain the word pink. Right? So it was, he likes to wink and drink ink. The word pink didn't occur there. So when I come to the word pink, I have to compute a 1 minus PW for it, the probability that it does not occur. Right? So that's just 1 minus the probability that it occurs. And I condition the occurrence of pink on its parent, and that is drink. And the drink did occur. So I take the probability of pink occurring given that drink occurred, and I take 1 minus that. That's the probability that pink doesn't occur according to this model. And then I have the word ink. It did occur in the document, but the parent did not. So there I need the second parameter. I need the probability that ink occurs in the document. So that's my second PW. That's the PW for when the parent does not occur. And if the word pink occurred, then I would use p ink given pink. Right. So is that totally clear? Yes. So this model allows you, with a fairly modest increase in the number of parameters, introduce conditioning into your probabilities. And now you're not making that silly independence assumption anymore.